So today we're going to learn some ancient wisdom about prime numbers. Before we do that, let's learn some tricks that will help us figure out whether a number is prime or not. So let's say you're looking at a number like 3879 and you want to figure out whether this number is prime. Now this is a pretty large number, and even if you use the efficient algorithm that I described earlier, it will still take you a long time to figure out whether such a large number is prime or not. So let me just tell you there are some tricks that you can use. So here's a list of tricks. These are called divisibility tricks that every essentially middle school student knows. So these are divisibility tricks. So the first trick is whether a number is divisible by 2. Okay, and division by 2, the very simple trick that you need to remember is that whether a number ends so in 0, 2, 4, 6, or 8. So the last digit is either a 0, a 2, a 4, or a 6, or a 8. So for example, if you have a number like maybe you want to figure out whether 4,846 is divisible by 2, and the answer is yes. Why? Because the last digit is 6, and 6 is an even number, and whenever you have an even number that ends a number, then it's going to be divisible by that number. So if I ask you another question like is 2083 divisible by 2, you look at this digit 3, and 3 is not a 0, 2, 4, 6, 8, hence it's not going to be divisible by 2. That's the first divisibility trick. The second divisibility trick, which is a bit more interesting, which is division by 3. So division by 3, how does that work? Well, the way it works is that let's say you want to test whether 471 is divisible by 3. Well, the way that you're supposed to do it is you actually divide by 3 and figure out whether there's a remainder or not. But the trick is that you add actually 4 plus 7 plus 1. So you're adding the digits, which are 12, and 12 does divide 3. So 12 over 3 is a whole number, and hence you conclude that 471 divides 3. And just to check, if you want to check whether 471 divides 3, you can check 471 divided by 3. 1 3s are 3, you get a 17, you get 5 3s are 15, and you get a 21, so which is 7 3s are 21, and you're done. So actually what you find out is that 12 does divide 3, and hence 471 divides 3. So let's do another example. Let's say you want to check whether, I don't know, a number like 400, we already tried 148, 149 is divisible by 3. So let's try whether 149 is divisible by 3. So if you want to find out whether 149 is divisible by 3, what you do is you add 1 plus 4 plus 9, that's equal to 14. 14 does not divide 3. So 14 over 3, that's what you check, whether 14 over 3 is a whole number and 14 over 3 is not a whole number. And then you conclude that 149 over 3 is not a whole number. And you can check 149 over 3 is not a whole number. Okay, so this is how you check divisibility by 3. Now if you want to check divisibility by 9, that's the same idea. So if you want to check divisibility by 9, you play the same game. So if you want to check whether 149 is divisible by 9, you do the same thing. So does 149 divide 9? What you do is you do 1 plus 4 plus 9, and you divide it by 9. That's just 14 over 9. 14 does not divide 9, and you can check whether easily that this implies that 149 over 9 is not a whole number. So this is not a whole number. So this does not divide 9. Okay. Now the last one would be 5. So this was divisibility by 9. And the last one is divisibility by 5. So this is divisibility by 5. And the way you check divisibility by 5 is that you check whether the last digit is a 0 or a 5. So let me give you an example. Let's say you want to check whether 2, 4, 5, 5 divides 5. Okay, so the way you check whether 2, 4, 5, 5 divides 5 is that you look at this 5, and since it's a 5, it's going to divide 5. So you check whether, essentially you want to check whether the number ends with a 0 or a 5. So if a number ends with a 0 or a 5, it's going to divide 5, and if it does not end with a 0 or 5, it's not going to divide 5. So for example, so this will divide 5, so this is correct. But if you have a number like maybe 92046, this will not be divisible by 5, and the reason why it's not divisible by 5 is because it's 6, and 6 is not a 0 or a 5, so this will not divide 5. Okay, so these are 4 divisibility tricks that you can use. I haven't explained to you the reasons why they're true. We'll try to understand them a bit later, but right now I just want you to know these 4 divisibility rules that seem to help people when they're trying to figure out whether a number is prime or not. But even given these rules, life is not easy. So if I ask you to tell me all the primes between 2 and 100, even with these divisibility rules and the more efficient algorithm, it will not be easy for you to figure out whether all the primes between 2 and 100. Now, a long time ago, there was this really cool guy by the name of Eratosthenes. So this is Eratosthenes, and he has a beautiful algorithm. It's a very efficient algorithm, Eratosthenes, and he's around 300 BCE. So he's quite close to the Pythagoras and the Euclids of his time. So Eratosthenes has this beautiful algorithm to figure out whether to figure out all the numbers between, let's say, 2 and 100, whether they're prime or not. The algorithm is very simple, right? We already know that 1 is just not an interesting number, so I'm going to get rid of 1. 1 cannot be a prime number. That's not interesting. Now what I'm going to do is I'm going to start out with 2, and 2 is a prime. So I'm going to circle 2, and 2 is a prime. Well, 2 is a prime, but I'm going to cross off all multiples of 2. So 4, 6, 8, 10, 12, all these guys are multiples of 2 because they end with a 2, clearly, and they end with a 4. I know divisibility rules, so they're all multiples of 2, they're all multiples of 2, so I'm going to cross off all multiples of 2. They are not going to be prime numbers, so I'm crossing off all multiples of 2. I crossed off all multiples of 2. And now the next number is a prime. That's what the algorithm states. The next algorithm, 3, is a prime. And now I have to cross off all multiples of 3. So let me cross off all multiples of 3. So 6 has already been crossed off. 9 has not been crossed off. So 9 goes, and then 12, 15 goes, 18, 21, 24, 27, 33, 36 is already gone, 39, 42, 45, 45 has to be crossed off, 45, 48, 51, and then I go to 57, 60, 63, 66 is already crossed off, 69, then 72 is already crossed off, 75, Then I'm going to jump to 78 is already gone, then 81, then I'm going to cross off 84, 87. I'm just crossing off all multiples of 3 right in front of you, 93, and then 96 is crossed off in 99. These are all multiples of 3, okay? So they are not prime because they're multiples of 3. And then 5, the next number is always a prime. So 5 will be a prime. And I'm going to cross off all multiples of 5, and that's very easy because all multiples of 5 are going to be ending up with uh, 5s or zeros. The zeros have already been crossed off. So then I'm done with all multiples of 5. And then I come to 7, and 7 is prime, and I have to cross off all multiples of 7. So if you know your 7 times table, it's 14, 21, 28, 35, 42, 49 is a new one. So let me cross this off. 49, and then I'm going to get to 56 and 63 and 70 and 77, and then I'm going to get to 84 and then to 91 and then to 98, and I'm done. So 7 is prime. And then 11 is going to be prime, and I will cross off all multiples of 11, and they're very easy: 22, 33, 44, 55, 66, 77, 88, 99. They've already been crossed off. And then 13 is a prime. And when 13 is a prime, I have to look at all multiples of 13. They are 13, 26, 39, and then I'm going to get to 13 fours, which is going to be 52. That's already done. 13 fives, which are 65. 13 sixes, which is 78. 13 sevens, which is 91. So I have to cross off 91. 13s. I should have crossed it off in 7, actually. I'm sorry, I made a mistake. For 7, I should have crossed it off at, because 13 sevens are 91, and I forgot to cross it off here. So I'm going to cross it here. 91 is also not a prime. So 13, and I'm done. There are no multiples of 13. And then I'm going to get to 17. Oops. And the 17 is prime. And 17 times table is very easy. 17, 34. 34 plus 17 is going to be 51. And then please note that I have already checked for 4, 5, 6, 7, 8, and 9, so I don't need to check any further, and I'm done. And then 19 is going to be prime for a similar reason, because I've already checked all numbers up to 19. I've crossed off all multiples of 19, and 19 times 18 is a very big number, so I don't need to cut off anything else. So everything else here, you can see, is now going to be a prime number because I have already checked all the smaller numbers, so I don't need to check now whether these guys are prime or not. So all these guys turn out to be prime numbers, and I figured out all the primes. Now the question is, obviously, why does this magic work? I want you to really think about it and see what a beautiful algorithm it is, and why does this algorithm work. And I want you to investigate with the help of your teacher and figure out why this algorithm is correct. Hope you enjoy figuring out this ancient mystery.